Problem number 21. A ping-pong ball, a hollow spherical shell with mass m, is placed on the ground with the initial velocity v0 and 0 angular velocity at time t equals 0. The coefficient of friction between the ping-pong ball and the ground is mu s equal mu k equal mu. The time the ping-pong ball begins to roll without slipping is next one. Solution for problem number 21. First, let's write equation for translational and rotational motion. Because this ping-pong ball is moving to the right with the initial speed, it will contact with the surface with the friction. It will decelerate with acceleration a. We can find from equation ma equal minus mu mg, where mu mg is a force of friction. And also we have rotational motion. For rotational motion we have I alpha equal mu mgr, where I is moment of inertia, alpha is angular acceleration, mu mg that's force of friction, and r is the distance from point of contact to the center of mass around which this ball is rotating. From here we can find that acceleration equal negative mu g, and because for hollow sphere we have moment of inertia equal 2 over 3 mr square. From second equation we can find what is angular acceleration. That will be 3 over 2 mu g over r. Now let's write equation for velocity and for angular velocity. For velocity we have this equation, velocity equal v0 plus at, and angular velocity equal alpha t, which is this one. Also, in time when this ball moving without slipping, we have v equal omega r. And now, using all these expressions, we can make equation 3 over 2 mu gt equal v0 minus mu gt. And from here we can find what is total time when ball begins to roll without slipping. That will be 2 over 5 v0 over mu g, which is answer A, and this is the solution for problem number 21. Problem number 22. A small hole is punched into the bottom of a rectangular boat, allowing water to enter the boat. As the boat sinks into the water, which of the following graphs best shows how the rate water flows through the hole varies with time? Assume that the boat remains horizontal as it sinks. Solution for problem number 22. By Archimedes' principle, the difference in the outer and inner water levels always remains the same. Then the amount of pressure forcing the water through the hole remains the same by Bernoulli's principle. So the rate of sinking is constant. That was answer A, and that was a solution for problem number 22. Problem number 23. The coefficients of static and kinetic friction between a ball and a ramp are mu s equal mu k equal mu. The ball is released from rest at the top of the ramp. Which of the following graphs best shows the rotational acceleration of the ball about its center of mass as a function of the angle of the ramp? Solution for problem number 23. This problem could be solved using excluding method. We can check that for zero angle, acceleration must be 0, because ball is stationary. It means that choice A is impossible and choice E is impossible. Also for 90 degrees, that must be 0 because there are no friction. it means that choice B impossible and choice D impossible. So we have only choice C left. And we see that here we have increasing angular acceleration with the angle increasing till some critical angle, and after it's decreasing to 0. So that's the solution for problem number 23. But also we can count it by formulas. For small angles we have no slipping. It means that linear acceleration proportional to angular acceleration and equal alpha r. We have a linear equation and angular equation describing linear and angular acceleration with using a force of friction. And from here, if we use a formula for moment of inertia, which in common case equal beta mr square, we have angular acceleration equal this expression. Here we can see that this angular acceleration increasing from 0 till some kind of a critical angle where we start to slip. And we can find this critical angle using a limit for force of friction. From one hand we can find that force of friction equal beta mr alpha, and from other hand we can put here maximum possible friction. That will be this expression. And from here we can find what is the critical angle. That will be this expression, 1 plus beta over beta multiplied by mu. When we increase theta more, we have motion with a slipping, and now we have to write different equations. Here we just use equation for rotational motion, and using formula I equal beta mr square, we can find that angular acceleration equal this expression. So we can use this expression for tangent theta more than this expression. And finally we have a solution for two cases. For both cases, small angles less than tangent theta less than this expression. We have alpha is increasing function, and for tangent theta more than this expression we have a decreasing function. These both functions, they are concave down, and also they have a sharp angle. So that's the definitely graph C. And this is the answer for problem number 23.